Hi, my name is Jingyi Chen. Today I'll be discussing Charge Coupled Device Sensor, which is CCD in short. In this video, I'll start with what is CCD and some current applications. Then I will introduce some history background, like how these genius scientists and engineers made this technology possible, and how this tiny device changed our life. Then I'm going to present some detailed description of the core principles. I'll finish with challenges for future development. So let's start. What is CCD? CCD is a device that can convert the analog signal of a light image into a digital signal. This picture is a simplified structure of one pixel in the circuit. CCD is made of thousands or even millions of these in array and array like a matrix. The purple dots here represent photons. Photons pass through the lens and interact with the silicon structure beneath. Electrons are generated through the photoelectric effect and then stored in the green part, a potential well. In a small pixel, charges are built up proportional to the light intensity. Now, photons are not only captured, but can also easily measured as voltage. Then through the analog digital converter outside of the CCD, we can successfully store an image as digital numbers. Where can we see CCD then? CCD image sensors are widely used in professional, medical, and scientific approaches where we need high-quality image data, such as single-cell imaging, astronomy, spectral telescope, and high-speed photographic technologies. This is one of the examples we call lucky imaging. Well, although CCD is a revolutionary technology in photography, and we widely use that in the beginning of like 20 and 21st century, some other image sensors became more suitable for our daily use. Since the late 2010s, CMOS sensor became the dominant technology, having largely replaced CCD. Well, what's the history behind this then? In the beginning, in 1887, German physicist Heinrich Hertz noticed the photoelectric effect. And then in 1905, Albert Einstein explained the law of this effect. Well, after that, in 1936, Radio Corporation of America invented the first photomultiplier tube, which is the official introduction of the image sensor. Then in 1969, Bell Labs was developing video telephony and semiconductor bubble memory technologies. Well, at that time, Willard Boyle and George Smith came up with the idea of CCD. They creatively combined these two technologies. They developed a device that can transfer the charge along the surface of the semiconductor. It is then later called the charge bubble device. In subsequent experiments, they discovered that the photoelectric effect could create an electrical charge on the surface of such device, which will then could be used to form a digital image. In the following times, hundreds of scientists and engineers worked hard to gradually bring CCDs to practical use. In 1975, Kodak made the world's first digital camera. It starts the digital era of the imaging product. Well, in the last century, photographic technology changed a lot, and until now, CMOS image sensor became the dominant technology. Well, what's the principles behind this? This is what CCD looks like, and these are some important components that comprise a typical CCD. It is a silicon-based integrated circuit consisting of a dense matrix of photodiodes that operate by converting light energy in the form of photons into an electronic charge. Electrons are generated by interaction of photons with these silicon atoms. They are stored in a potential well, the green part, and then subsequently transferred across the chips through the registers and output to an amplifier. The most important part is the MOS capacitor. In general, there are two types, one having a surface channel structure, while the other one have a buried channel design. In CCD, we use the second one. The MOS capacitor array is fabricated on p-type silicon, in which the main charge carriers are positively charged electron, called holes. When the capacitor is unbiased, the electrons in the N region of the device will equilibrate to the lowest potential energy. Well, in this equation, Q stands for the magnitude of charge density, and the phi is electrostatic potential. Well, a potential diagram is like this. Well, this means that the electron is gathered about 1 micrometer beneath the oxide layer, like here. When the CCD is exposed to light, each image element has an electrode at a high potential. The potential under this electrode in the silicon wafer will increase and become the place where the photon electrons are collected, which we call it a potential well. The electrode near it form a potential barrier and defines the boundary of this image element. So now what we would do to get the image from a matrix of this? Well, the most straightforward way would be to use wires to connect each pixel, and we can read the information one by one, like measure the charge on each section. This makes sense, but all the electronic components leaks a little bit charge that distort the image. Well, CCD solved this problem in a rather simple way. There is no wires attached to each pixel. Instead, we make the electrons move array by array to the output. Each row of electrons is shifted downward using a positive voltage. The electrons are shifted by spreading the positive voltage over neighboring pixels to transfer them to a new pixel. This will continue all the way down to the sensor until they are transferred to the readout register. Once they reach the readout register, the electrons are shifted horizontally, column by column, where they are amplified and digitalized. This process is repeated one by one until the whole sensor is cleared. Then the sensor can be exposed to light again to acquire a new image. Well, this apparently has some drawbacks. We only have one output. This means that this process will introduce noise to each pixel, and electrons will repel to each other if we transfer it too quick. This limits the speed. Well, thirdly, the entire sensor needs to be cleared of electrons before the next exposure. Well, for example, some CCD require mechanical shutter to block the light. Well, to try to minimize these limitations, we have several different CCDs. Well, the first example is called frame transfer CCD architecture. In this example, half of the pixels are not for exposure. They're called storage array. While this storage array is being read by the system, the image array above them is ready for next exposure. So this allows for continuous operation without a shutter. Well, the second one is called interline transfer CCD architecture. And there are alternating straps that allow a rapid shifting of any accumulated charge as soon as the exposure is complete. Then what is CMOS? We mentioned it earlier at the beginning, which now largely replaced CCD. CMOS is called complementary metal oxide semiconductor. CMOS is really similar to CCD, but each pixel has its own charge to voltage conversion, and the sensor often includes amplifiers, noise correction, and digitalization circuits, so that chip outputs is digital bits. Well, another example is called EM-CCD, which is electron multiplying CCD. This utilizes on-chip multiplication gain technology to increase the number of electrons generated from photons. This process occurs before the charge reaches the output amplifier, so the signal is increased before the read noise is applied. This technology can achieve like single photon detection with relatively low noise. And now we've talked about CCD and CMOS, and we know that CCD is now largely replaced by CMOS. Why is that? What is the advantages and disadvantages of both of them? Well, first of all, although CCD can have higher quality and lower noise, but it is more expensive to manufacture one and also consume much more energy than equivalent CMOS, CIS. And also, CCD has a relatively low integration level, which means that CCD only can output an analog electrical signals. We need many more steps to process this information. Well, compared to CMOS, it can integrate all the modules on one chip, and it also has higher readout rates and lower power consumption. Well, after entering the 21st century, due to the rapid development of fabrication technology, the CMOS performance gradually reached and even surpassed CCD. It now is a mainstream image sensor. Like in this diagram, CMOS accounts for nearly 85% of image sensor in the market. Well, like in 2024, maybe it will probably reach 90%. Well, I believe CCD will, on the other hand, focus more on scientific use. Well, that's all. Thank you.